Hello everyone, my name is Xiangyu Wang. I'm a graduate student from RPI. Today I want to talk about nanomaterials. I will introduce a couple characterization techniques combining with the project of the study of silicon carbide and carbon coaxial nanocables. This presentation is part of my course Nanostructured Materials taught by Professor Ziegel. Nanomaterial is the field of the study of materials with morphological features on the nanoscale, especially those which have special properties stemming from their nanoscale dimensions. For silicon carbide one-dimensional nanostructure, it has attracted considerable interest due to their contribution to the understanding of basic physical concepts under Shell's confirmed field. In addition, it also has great potential applications in high-temperature, high-power nanoelectronics, and field-emitting devices. In my experiment, a mixture of SiCl4, C6Cl6, and sodium were loaded into a stainless steel autoclave. SiCl4 and C6Cl6 was the source material, and the sodium was used as a reductant. The autoclave was sealed and heated in a furnace to 250 degrees within 1 hour, then held at that temperature for 6 hours. When the autoclave was cooled to room temperature, the product was collected. Subsequently, the product was washed with absolute alcohol, diluted hydrogen fluoride, and distilled water, intended to remove sodium, silicon, sodium chloride, and other impurities. Finally, after drying in a vacuum oven for 4 hours, a black and blue sample was obtained. Then, we will go to the characterization to see what we have. First comes the X-ray diffraction. X-ray diffraction finds the geometry or shape of a molecule using X-rays. X-ray diffraction techniques are based on the elastic scattering of X-rays from structures that have long-range order. For this project, from XRD, it can be seen that the original product without purification are composed of sodium chloride, silicon carbide, and silicon. After the washing treatment, the strong intensity peaks in XRD pattern could be indexed to the cubic zinc blend structure of silicon carbide. Impurities such as sodium chloride and silicon were not detected in the sample after the washing treatment. After XRD, I want to study the morphology of my product. I use transmission electron microscopy, TEM. TEM is a microscopy technique whereby a beam of electrons is transmitted through an ultra-thin specimen, interacting with the specimen as it passes through. An image is formed from the interaction of the electrons transmitted through the specimen. The image is magnified and focused onto an imaging device. The TEM images reveal the morphology of the sample. The length of the one-dimensional nanostructure is up to 1 micrometer, and the diameter ranges from 40 to 60 nanometers. The phase contrast is different between the inner core and outer shell, suggesting a coaxial nanocable structure. Moreover, an interesting orientation accumulation of tapered crystallets in the core region can be distinguished clearly. Furthermore, if we want to see more and clear details, we need to seek help from high-resolution transmission electron microscopy, HRTM. HRTM is the imaging mode of TEM that allows the imaging of the crystal structure of a sample at atomic scale. Because of its high resolution, it is an invaluable tool to study nanoscale properties of crystalline materials. Here, HRTM depicts the details of a typical coaxial nanostructure of the nanocable. In the core region, the phase contrast is deep. The base length of the tapered crystallates is about 40 nanometers, and the height is about 20 nanometers, while the thickness of the outer coating layer is about 10 nanometers. The clear lattice fringes and the selected air electron diffraction pattern of the core region in Figure C illuminates its single crystalline nature. The fringe spacing is about 2.52 angstroms, which corresponds to the 1-1-1 plate spacing, indicating the nano-ones glow along this direction. The hollow-like selected air electron diffraction pattern in Figure D shows that the outer shell is almost amorphous. Then, I use element mapping to verify the core shell structure assumption. Element mapping displays the elemental image of a single nanocable, with the bright region representing a high concentration of a given element. Using energy loss of the K-shell edge, the elemental mapping of carbon shows that the carbon component is distributed all over the inner and outer region, while using the energy loss of the L shell edge, the silicon elemental mapping shows that the silicon exists only in the core region. Till now, combining XRD, TEM, HRTM, and elemental mapping analysis, it is confirmed that the crystalline center core of the nanocable is beta silicon carbide, and the shell layer is composed of amorphous carbon. Based upon the above characterizations, the possible growth mechanism and chemical reactions leading to the synthesis of silicon carbide and carbon nanocables are proposed as follows. First, the sodium could reduce C6CO6 to delete chlorine under mild conditions, according to the Woods reaction, and without destroying carbon and carbon bonds as shown in the first reaction. Then, the newly produced carbon clusters provide the basic carbon source for silicon carbide nanostructures. At this time, at preferred growth sites, silicon carbide spaces nucleate and aggregate to form nanowires. In the later stage of the reaction, the heat provided by the furnace would be insufficient to break carbon and carbon bonds. Carbon produced by the reductive reaction would be deposited on the surface of the silicon carbide nanowires as the amorphous shell. Thus, silicon carbide and carbon coaxial nanocables could be formed. I want to thank Professor Zhai and Professor Chao. Without them, I can never finish this work. And I also want to say thank you to Professor Ziegel. He gave me this opportunity to share my work with all of you around the world. I really hope you enjoy it. Thank you very much.